Good afternoon, everyone. This is the problem solving session for the NPTEL course Fluidization Engineering. So, since this is the first session, let us wait for 5 more minutes so that we can see someone will be joining us. I'll just share my screen. So, yeah, we'll start. I think already 3-5. If anyone joins, we'll let them in. So, yeah, welcome. I welcome you all to the first session for the NPTEL course Fluidization Engineering. So in these sessions, if you are familiar with NPTEL already, you would be probably knowing that these problem solving sessions are conducted to help you in solving the assignment problems. So it is kind of aid in the assignment solving. And also in this, if you have any other doubts which you want to clear, we can clear in these sessions as well. So these sessions are for that purpose. So uh, this is since this is the first class, we'll be solving the problems related to the first week's assignments, and also like we'll be having an overview of what this problem solving sessions will be covering, because as you probably are aware already that the course instructor would be giving you the lectures for the course, which you'll be having in the NPTEL website, wherein you need to access that for the complete lecture videos. So on accessing that, you will get an idea of what is being taught in the class. So after that, you'll be having the assignment submissions every week. So for every week assignment submission, you will be required to submit the assignments. So for those assignments, these sessions will be helpful because we'll be solving similar problems. So these problems will be actually helping you in getting the hands on that. And so we'll see as the session goes. So I want you all to be very open and ask questions whenever you have. And if there are any doubts, you can just ask in the next class also. So I just want to give an idea on that. So apart from this, if you have any concerns regarding the session, you can always share. And also, yeah, that's it. So we'll start the session. So I'll just present my screen now. So as you all know, this is an NPTEL course, and the course is Fluidization Engineering, and this is the first problem solving session for this course. The course code is given over here, and the course instructor is Professor Subrata K Majumder from IIT Guwahati Chemical Engineering Department, and myself Ankara Karthika from IIT Hyderabad. So I am a research scholar. So my area of interest is fluidized beds. So if you have any concerns or any doubts, I'll be happy to help. And this is our first session, and today we'll be having the session running from 3 p.m. to 5 p.m. So yeah, before going into the problems, first let us first see what the course layout is. And here we have week 1 to 2. In week 1 to 2, we'll be covering the introduction to the fluidization phenomena and the advantages and disadvantages of fluidized beds, industrial applications of fluidized beds. And second week, it is about the characteristics of solids, classification of solids, flow characteristics, and its outline in different types of fluidization. And 4 to 5, it is about flow patterns of fluidization systems and flow pattern transition. So flow pattern transition, flow pattern map, because in fluidized beds the most important thing is solids, and we need to identify the characteristics of the solids. So we need to know in which regime of fluidization it would be having, and what types of, what are the properties of the particular solid. So it would be easy for us to analyze the movement, mixing, segregation, whatever it might happen. So the classification of solids help us analyze the situation happening inside the bed and get hands on in what is the mechanism or what type of things would be happening inside the fluidized bed, because mixing, segregation, everything is there, and so it would be helpful. And in uh, along week 6, we would be studying the gas distribution and different types of gas distributors. And week 7, it would be bubbling fluidized beds. So as we go along the class, you will be seeing there are different types of fluidization regimes by classified based on the inlet fluid velocity. And 8, it would be entrainment and elitration from fluidized beds. And 9, it is attrition mechanism. And 10 to 11, it is mass transfer phenomena. And from like particle to gas mass transfer phenomena. And at the end, we'll be dealing the heat transfer phenomena. So main thing I want you to focus on is understand the concept of fluidization thoroughly, because fluidization in BTech level of chemical engineering we would have studied it as a part of a subject, but we would not have gone in depth into it. So this particular course would help you analyze, and it can be taken as an elective also if you have got it in your class. And there is a wide scope of fluidized bits in the industry wise. So knowing and understanding the fluidization concepts is very essential. So yeah, and for reference books we have Kuni and Levenspil's Fluidization Engineering. Why no one else is joining? I just want to know. Hmm. People, if you have any concerns, please let me know, because this is the first class. At least I hoped 10 to 15 people to join, but that is not the case. It's okay, we will just see. If you are watching this video also, and if you have any concerns or any doubts, you can join the class and ask. It would be beneficial for both of us if you join the class, because I could be explaining more in a way that you people understand in the live class than in through any other means. Like forum is also there where you can post your doubts, but it would be very time consuming process. Rather than that, we can discuss one on one in these classes. So my suggestion would be to please attend the class and get help in solving the problems. So yeah, books and references. First one we have is the Kuni and Levenspil's Fluidization Engineering. This book I would completely recommend you people, because it covers all the basics required for understanding the concept of fluidization. And if you have read the book, you would be like understood the fluidization basics completely. And next is Giraspo's multiphase flow and fluidization continuum and kinetic theory description. So when we are modeling or designing the fluidized beds, there is what we have in fluidized beds. So we have a fluid medium and the particle medium. So it is, we all know that through CFD we get the modeling for the fluid part, but how are we supposed to get the modeling for the particles? So there are two ways to model the particles. One is Lagrangian motion, wherein each particle is tracked individually. And next is Eulerian motion, wherein it is assumed as a continuum. We all know that particles are not continuum, but in Eulerian method, particles are assumed continuum and are modeled based on that. So how are we modeling the particles when we assume it as continuum? We all know that we have kinetic theory of gases. Similar to that, we have kinetic theory of granular flow, KDGF. So this explains the mechanism or flow behavior in the fluidized beds. And this book basically covers all the requirements regarding that and helping us understand that. And third, we have Gibbelaro's fluidization dynamics. And fourth, we have S K Majumder's hydrodynamics and transport processes of inverse bubbly flows. So moving on to that, we'll go with this week's problem. So before that, I want you all to uh, know what is fluidized beds. By now, you people would have seen the lectures and are very familiar with the concept of fluidized beds. But can anyone explain what is fluidized beds? So I guess this question, even though you people might be aware of what is fluidized beds, but maybe if anyone answers, I would be happy. Like one person is there, maybe they can answer. Okay, if not, I myself will do that. Fluidized beds are nothing but wherein it is a like device, or I mean it is an equipment wherein some means of separation or some mechanical operations, it is a mechanical operation device or something. Not just mechanical, you can do unit operations and unit processes as well. So here we have a fluidized bed, that is a packed bed. By packed bed, we all know that we have a column and it is filled with particles. And consider we are passing air from the bottom of the bed, and the bed particles doesn't move at all. So can you people just imagine what I'm trying to say? So here we have a column. Consider this as a column. And we are packing still here. Like till here we have particles packing. And just don't bother about my worst drawing skills. But we have particles packed till here. So this is known as packed bed, and what are we doing? We are passing the air from the bottom of the bed. And if the air or the fluid escapes through the voids in between the particles, so particle packing will also always have some space between them, and if the fluid is passing through that and the bed height remains the same, that is this height remains the same, even at whatever velocity we are passing, so this is known as packed bed. But if this particular bed starts to increase in height, that is the particle starts to move. So when particles move, what happens? The bed is becoming fluidized. That is, the solid particles are now behaving like a fluid. So can you people imagine what I am trying to say? I have one slide on that. So this is what I am saying. So here we have particles packed inside the system, and we are passing the air inside the bed, and we have in the packed bed the air passes through the voids between the interstitial air, the voids between them, it starts to move. Whereas in fluidized beds, the particles itself will start to move. When will that happen? When the air velocity has crossed a certain minimum fluidization velocity, we call that. So when it has crossed certain velocity, the particles will start to move. So that particular velocity is known as minimum fluidization velocity, that will be covered in the coming up classes. And so we have our packed bed has now transformed into a fluidized bed. So this phenomenon is known as fluidization. So what happens when these particles starts moving? So imagine that in the packed bed, we have particles are tightly held and there is no movement of the particles. So for example, what I'm saying is that consider this box. So here it is packed till the particles are packed till here, and when here we are passing air from this. So when air is tightly packed, the particles will be packed until this height, and there will be no movement of the particles in the packed bed. So what happens? The surface area or the area of the particle in contact with the fluid is very less, right? Whereas we have increased the velocity to some extent, so that at this particular condition, what has happened? The particles have started to move. So the particles have started to move and it has reached from this height to this height. So at this position, the particles are behaving like a fluid, we say, and it is known as fluidized beds. So even at such high velocity, chances are there the particles will be going till if the column is very high, the particles will be going at more height. So this is known as fluidization. And if the particles are reaching more height from this particular height, what happens? We are able to see that the surface area of the particles that are being in contact, surface area of the particles that are being in contact with the fluid is very less. I mean, which was less in the packed bed has increased in the fluidized bed. So that's what we call as fluidization. And advantages, we have increased surface area, and also the particles have started moving, so the mixing contact area has increased and the mixing efficiency is increased, and so on. So we say that fluidization is an advantageous phenomena. So coming back, do we have no disadvantages when we are, I'm sorry, why isn't it going? Okay. Just a minute, my mouse has got hanged. Okay, it is there somewhere. Okay. Why it is giving a big screen actually? Okay, whatever. We'll just deal with it. Yeah, thank God. So what we were saying, so it has an increased surface area, and also the mixing behavior is promoted, everything. So is that the advantage of fluidized bits? Sure, it is the advantage. But does it mean that there is no disadvantage associated with the fluidized bits? No, it doesn't mean that. And we have certain limitations also when we are dealing with fluidized bits, like the particle, since it is moving at a high speed, chances of the particles escaping the column is high, and also the particles will rub against each other, and because of that the material loss, everything will be there. So these are certain disadvantages and certain advantages also there. So at the end, it always comes down to what as our requirement and how much we are able to compromise on certain things. That is what matters at the end of the day. So yeah, now we'll start with the questions for this week session. So if you have any doubts, you can stop me in between any time. And apart from that, we'll have doubt clearing session at the end always. So we'll start with the questions. And if you people have answers, you can always say the answers also in between if you are willing to say. And or you can put it in the chat window also, like your options. We can check if required. Yeah. And yeah, so we'll start with this class. So the question one is, fluidization is a process similar to the liquefaction, whereby a granular material is converted from a static solid-like state to a dash, which occurs when a fluid is passing through the granular material. So this is just a definition of fluidized bed. So we have seen just now what it is. I mean, what fluidized bed is. So what is fluidized bed? Fluidization is a process of converting a solid to fluid. That is what we given a single line. But previously, what was the state of the solid? It was static. The particles in the packed bed were not moving. And now in the fluidized beds, what it is state, it has more, the particle starts moving and it is a dynamic nature. And now instead of having the solid like behavior, these particles started having fluid like behavior. So we'll see the options and then we'll come back to the answer. First one is static fluid-like state. Second one is dynamic solid-like state. Third one is dynamic fluid-like state. And fourth one is granular solid-like state. So the answer we know is, do you want to take a minute to answer, or we can go with the answer? I think today's class we'll go with the answers, but in the next week class we can always have some time for you people to come up with the answers. So for today's class it is dynamic fluid-like state. So the answer is dynamic fluid-like state. So what have we got from this particular question? It is that the fluidization is a process similar to liquefaction, wherein the granular material is converted from a static solid-like state to a dynamic liquid-like state. So in the packed bed condition, the particles were not moving, but in fluidized beds, the particles started to move and they started behaving like a fluid. So these are two important things in fluidized beds. That is, they behave like a fluid, which is why we call it as fluidized beds. That is, we have fluidized the solid particles, and second is they are having a dynamic nature because they keep on moving. So we have the right answer as option C or 3 or whatever, dynamic fluid like state. So now we'll go on to question 2. In question 2 we have, in fluidization, which among the following is a gas phase non-catalytic reaction? So in fluidization, which among the following is a gas phase non-catalytic reaction? So first one option is hydrotreating, hydroprocessing. We'll first look at the options and then we'll come up with the answer. So the first one is hydrotreating, hydroprocessing. Second one is acrylonitrile and aniline. Third one is roasting of ores, and fourth one is natural gas combustion. So these questions or these things you have actually seen in the lecture itself. So you people are by now aware of the answers. So here what is the key thing to be noted or key thing to be taken? We have two keywords in the question. The first one is gas phase and the second one is non-catalytic reaction. So acrylonitrile, everything is the catalytic reaction, and hydrotreating, hydroprocessing also involves catalyst, and roasting of ores is a gas solid phase reactions because solid is also playing an important role over there, whereas natural gas combustion is a gas phase reaction because the reactants and products of our interest is gas phase. So the answer to this question is natural gas combustion. That is option 4 or last option is the right answer. That is, we are looking at the natural gas combustion. So question 2, in fluidization, which among the following is the gas phase non-catalytic reaction? And the answer is natural gas combustion. So now we move on to question 3. Okay, yeah. In question 3, we have in a particle size analysis, the following results are obtained. Volume, surface, mean diameter of the particle in micrometer is. So what is being asked? We have performed the particle size analysis and the results are obtained, and we need to find out the volume, surface, mean diameter of the particles. So whenever in the industry, do you think the particle size will be uniform throughout? For example, you have taken some what to say, whatever the settling study or okay, let us consider fluidized beds itself. You are fluidizing a coal particles. So do you think the all the coal particles inside the fluidized bed would be of the same size? No, right? They won't be of same size. Each particles would be in different size. For that, we need to have an understanding of how we can quantify the size of the particles. So for that purpose, we do particle size analysis. Simple thing would be like doing it in the sieve shaker and getting the size range of particles and the mass of particles in that size range. And more things are more advanced things like laser size analyzer are there, wherein we feed the particles and it would give out the size range of the particles in the system. So here in this particular question, similar size particle size analysis is performed and the following results are obtained. So we need to find out the volume, surface, mean diameter. So what is given? Mass of the particles in gram and the corresponding mean size of the particles in micrometer are given. So for 2 grams of particles are in 350 micrometer size, and 5 grams of particles are 240 micrometer in size, and 7 grams of particle are 200 micrometer in size, and 4 gram of particle is 150 micron, and at last 1 gram of particle is in 100 micrometer size. So now we need to find the volume, surface, mean diameter. So options given are, first one is 199.986 micrometer, second one is 193.986 micrometer, and third one 190.986 micrometer, and fourth one is 195.986 micrometer. So I would like to add one more point here. This question was asked in the GATE 2016 or 2015 somewhere. So like Some questions from here would also be appearing in gate because it is similar to what you have studied in mechanical unit operation actually, the particle size analysis part especially, and some concepts you might have studied in and it would be appearing in gate. So just some concepts would be very common, like particle size analysis is very common, which you would have studied, and try to bring in those concepts which you have studied into application oriented things. For example, as I said, the particles you would be using in fluidized beds would not be of the same size. So at that time, how would you find out the mean particle size? You would be doing some sort of particle size analysis, and for different applications again we have different types of diameter which we would be using. The question here is regarding volume surface mean diameter, and there are several other diameters like mass mean diameter, arithmetic mean diameter, and so on and so forth. So depending on the application you will be requiring different type of things. So coming back to the questions, I guess the answer is around 193. Yeah, 193.986. Do any one of you want to solve the questions? You're free to welcome and you can give us the answer. If not, we'll just take a minute to think of, and then we'll get back to the answer in the next slide. Answer meaning answer like we'll be taking steps and giving out the solution. So the first one, before you solve any of the problems, first you need to do two things. First, write the given. You people might have aware of everyone around you saying this before the exam. Just follow the step-by-step procedure. So the first one is always write the given, and next write the formulas associated, and then go to the solution, because whenever you are attempting to do these things in the exam it would give an impression that you are very aware of what you are doing, rather than just going directly into the flow. You may be aware of what is happening in the problem and you may be directly jumping into the solution, but that is not always the case, and that would give you an impression, I mean wrong kind of wrong impression to the correcting authorities also, when you are writing a long answers in the exams. So always follow procedures, that would be better, and it would be giving you that you are having so much clarity, and you would also be very confident when you go with that. So we'll follow that same thing over here, and yeah. So here we are given the mass of the particles and mean size of the particles. So yes, here what we are doing. We are writing given, and yeah. So given we are having mass of the particles in gram, and we are calculating the mass fraction of the particles. So total mass is what is here, 25714 gram, and mass fraction we are dividing the mass of the particles in that particular size range divided by the total mass of the particles. So here it is 2.2 by 19, 5 by 19, 7 by 19, 4 by 19, 1 by 19. Yes. And what are we doing then? Yes. And then we are okay. Mentioning the mean size of the particles already given in the question, and then we are calculating xi by dpi. So mass fraction is xi, which we have calculated, and dpi is nothing but mean size of the particles. So we are dividing 0.1053 divided by 350 and we are getting this, and similarly 0.2632 divided by 240 we are getting this, and 0.3684 divided by 200 we are getting this, and 0.2105 divided by 150 we are getting this, 0.0526 divided by 100 we are getting this. And volume surface mean diameter, here the formula is d is equal to 1 by xi by dpi. So 1 divided by summation of xi by dpi from I is equal to 1 to n. So what are we supposed to do? Xi by dpi we need to find out, and at last we need to add up all these to get the summation of xi by dpi from 1 to 2, 1 to n. N here is 5. So here we are adding up all these values and the total sums up to 5.1689, and 1 divided by 5.1689 into 10 power minus 3 gives us 193.4648 micrometer. So I hope you are clear with the question. We will see the question once again. So what is given in this question? Here it is particle size analysis of the samples is given, and the following results are obtained. And volume surface mean diameter is in micrometer. So we have 25741 grams of particles with a corresponding particle size given in the next row, and we are asked to find the volume surface mean diameter, and for that we have calculated the mass fraction of the particles first, which how did we calculate? We calculated by dividing the mass of the particles in that particular size range divided by the total mass of the particles. So we have got the mass fraction, and we have then calculated xi by dpa, and we have summed up these values which comes around this, and then we have volume surface mean diameter formula, which is given as d is equal to 1 by xi by di, and d is equal to 1 by this value, and we are getting 193.4648 micrometer. So this is how we got the answer for this particular question. And now I think it is clear now, so we go on to question 4. In question 4, it is asked that calculate the sphericity of the cylinder of diameter 1 centimeter and height 3 centimeter. So what do we know about sphericity of the particles? So we all know that in whatever theory you study in class, you'll be dealing with spherical particles. Like, for example, in fluidized beds itself, if you consider, it is easier to study the phenomena of fluidization by considering the particle shape as spheres rather than non-spherical particles. First thing, why is it difficult to study non-spherical particles? Because imagine you have a sphere. How many parameters are required to describe the shape of the sphere? You require only one, that is radius. And with radius as a parameter, you can get almost all the information of the particle. Surface area you can get, and volume of the particle you can get, and whatever you require you will be getting. And you can describe this shape of the sphere by using radii. But when we say non-spherical, do we have a category of something like that? Here we are dealing with the non-spherical particle cylinder. Cylinder we can define it using length and the diameter of the cylinder. And if it is a cube, we can say it using side length. And if it is a cuboid, again we have 3 dimensions, and with that we can say. And if it is, imagine if it is hemisphere, again we can say with radius is a parameter, but with the different things. So each particle shape has its own set of parameters. So there are no single parameter which is defining all together, and it is putting together putting everything together. So it is always difficult to imagine the particle shape, and what I have said now is only for regular shaped non-spherical particles. There are n number of non-spherical particles which are irregularly shaped. Consider as sand or broken glass pieces or whatever. Like for example, some dal you can take. Those should be like for example, chana dal if you take, we can say it is a hemi-ellipsoid, but each particle is not very uniform in shape and size. And also sand, as I told, like some sands would be sharp and some would be like similar to sphere. So each particle has its own set of parameters, and some particles might be very irregular. For example, you cannot define the structure of a shape of the sand using any means, or you cannot define the shape of the broken glass pieces by any means directly. So these are all irregular particles. So something to club together every non-spherical particles, we needed a concept. So that concept came in the form of a sphericity. So here we have sphericity requirement, And sphericity is nothing but the ratio of the surface area of the volume equivalent sphere to the surface area of the particle itself. So this shows us how much the particle is close to sphere or it is deviating from the sphere, we can identify. For example, if it is 1, it is sphericity of 1 means that it is a sphere, and sphericity less than 1 means it is non-spherical particles, and if it is less than 0.64 it is very highly irregular shaped particles. So now we are asked to calculate the sphericity for the cylinder whose dimensions are given for length and diameter, that is height and the diameter or length and diameter. So first one is 0.749, second one is 0.759, third one 0.779, fourth one 0.729, and answer is 0.779. So for this particular reason we are now going to calculate the sphericity, and we'll see this in a step by. As always, since this is a problem, we need to first write the given over here. So given is cylinder, particle shape is given as cylinder and its diameter and height is given as 1 centimeter and 3 centimeter respectively. So first we are calculating the volume of the cylinder. First, always we need to know, so sphericity is defined as surface area of sphere with same equivalent volume to the surface area of the actual particle. So that is how we define sphericity. So for that, we need to calculate the surface area of the actual particle and surface area of the sphere with same equivalent volume. Meaning, we need to find the volume of this particle. So volume of cylinder, volume of actual particle, that is cylinder, is equal to pi r square L or pi by 4 d square L. So here we have got it as, I better put it as 1 by 2 into square is 3. That is, we are getting 2.355 centimeter cube. And surface area of actual particle, that is cylinder, again, how do we, what is the surface area of cylinder? We have the outer perimeter is 2 pi RL, and both the top surface and the bottom surface we have pi r square. So it is 2 pi r square plus 2 pi RL. So we have taken 2 common and also pi common. 2 into pi into r square. So r is, first one it is 1 by 2 and again 1 by 2 square, and here it is 1 by 2 into 3 pi r square and pi rl. Surface area of actual particle is 10.99 centimeter square. And volume of sphere formula is 4 by 3 pi r cube. And volume of equivalent sphere radius. So here we need to volume of actual particle. Why are we doing this? To find the volume equivalent sphere. So volume of sphere is equal to volume of this, and it is equal to 2.355 centimeter cube. So now we know as volume equivalent sphere radius is 2.335 into 3 by 4 into pi into power 1 by 3. It gives us 0.8255 centimeter. So surface area of sphere with same equivalent volume is equal to 4 pi r square. So this r comes from volume equivalent sphere radius, right? And you substituting this, and sphericity you are finally calculating as this. I hope you are understand. If not, we'll just go through this one more time. So here what are we asked to calculate? We are asked to calculate the sphericity of the particles. So the first one is we need to know two things when we are dealing with the sphericity of the particle. So first one is we need to know the surface area of the particle and the volume of the particle. And the second one is we need to know the surface area of the sphere which has the same volume as the particle. So first let us calculate the volume of the actual particle, and this is volume of actual particle and this is surface area of actual particle, and it is pi r square L, and we have calculated the volume of the actual particle and the surface area of the actual particle. Keep in mind we have calculated two things from the original geometry of the particles, that is we have calculated its volume and we have calculated its surface area. And now we need to identify the equivalent radius or diameter of a sphere. That sphere has the same volume as that of the particle. So what are we doing here? We have the cylinder and we have the volume of cylinder to be 2.355 centimeter cube. So we need to know how much would be the diameter of the sphere if it has the same volume, that is if it has 2.355 centimeter cube as the volume. So now the volume of sphere and the volume of the cylinder is the same. So if that is the case, what would be the radius of the sphere? So for that we have calculated the volume of sphere 4 by 3 pi r cube, and 4 by 3 pi r cube is equal to this, and now we have calculated the sphere volume equivalent sphere radius, and it is 0.855 centimeter cube, and now we have calculated the surface area of the sphere with the same equivalent radius. So and now we got the surface area of sphere with same equivalent volume. So it is 8.559 centimeter square. Always remember that the sphere surface area of sphere would be the highest and surface area of non-spherical particles would be lower. So here surface area of sphere with same equivalent volume is sorry, I think I missed it. Surface area of the sphere would be the lowest and surface area of the non-spherical particle would be highest. I mean not highest, higher than the spheres. So surface area of particle with same equivalent volume and divided by surface area of the actual particle gives us this 0.7788. So surface area is 0.7788 or 0.779. So answer is option C, that is 0.779. So I hope you are clear now. First, what have we done? We have first calculated the surface area and the volume of the actual particle, that is cylinder, and on the basis of the assumption that volume of the newly constructed sphere is equal to the volume of the actual particle, that is cylinder, what would be the volume of the newly constructed cylinder? Newly constructed sphere, it is the volume of the cylinder. So what would be the radius of the newly constructed sphere? So we have back calculated the radius, and from this particular radius we have calculated the surface area of this sphere, newly constructed sphere. So sphericity is defined as the ratio of surface area of the newly constructed sphere with same equivalent volume divided by surface area of the actual particle. So on dividing this and doing the calculations, we are able to get the sphericity value as 0.7788 and our required answer is 0.779. So yeah, that is the answer. So now we are moving on to question 5. In question 5 we have zeta potential. Zeta potential is defined per Smolukowski equation as zeta is equal to mu z eta divided by epsilon r square epsilon naught. Second one, zeta is equal to mu z eta divided by epsilon r epsilon naught. And 3 is zeta is equal to mu z eta divided by epsilon r epsilon naught square, and fourth one is eta is equal to eta divided by epsilon r epsilon naught mu z. So what is zeta potential, that we will see in the question in the coming up slides. Now we need to identify what is the zeta potential. Definition as per the Smolukowski equation. So that is answer is coming as option B, zeta is equal to mu z eta divided by epsilon r epsilon naught. So that is the zeta potential. So we will see more about zeta potential in the coming up slides. So now we are going to question 6. In question 6 it is given that powder's tendency to gain or lose moisture at a constant temperature is important to understand the caking behavior signifies. So what does powder's tendency to gain or lose moisture at a constant temperature is important to understand the caking behavior signifies. Option 1, transportable moisture limit. Second one, dust extinction moisture. Third one, moisture sorption or desorption. Fourth one, saturation moisture content. So what does the powder has a tendency to gain or lose moisture at a constant temperature. So why is it important to understand this? Uh, so why would we know or what it is signifying? So first one is transportable moisture limit, second one is just extinction moisture, third one is moisture sorption or desorption. So here it is third one, and fourth is saturation moisture content. We are going with option 3 because gaining or losing moisture at a constant temperature is given. It's important to understand the caking behavior signifies moisture sorption or desorption. So we'll see why in the next slide. In question 6 it is given that transportable moisture limit, it signifies the evaluation behavior of material liquefaction behavior, and dust extinction moisture, it is the moisture at which material does not emit dust, and third one, moisture absorption or desorption. Powder's tendency to gain or lose moisture at a constant temperature is important to understand the caking behavior. So this is our answer, and the last one is saturation moisture content, which is the maximum moisture material can withstand without it becoming slurry. So we have learned four new terms today. I mean, you would have already learned it from the course. So first one is transportable moisture limit. So this transportable moisture limit is nothing but evaluation of the liquefaction behavior of the particles or the material. Second one is dust extinction moisture, and that it means moisture at which material does not emit dust. And third one is moisture sorption or desorption, which is what is studied over here. It means that the powder's tendency to lose or gain moisture at a constant temperature. And the last one is saturation moisture content, the maximum moisture material can withstand without them becoming slurry. I hope these terms are self-explanatory, but I've just given the what these terms mean. And our requirement is powder's tendency to gain or lose moisture at a constant temperature is moisture sorption or desorption. So again, coming back, we have one more problem. I think it is, yeah, we'll finish this problem and just take a 5 minutes break, and then we'll come back. Okay, question 7 is nothing but calculate the surface volume mean diameter for the following particulate material. So we have size range in -104 plus 352 minus 352 plus 176 minus 176 plus 88 minus 88 plus 44 pan. And mass of the particles in that range is given over here: 25 grams, 37.5, 72.5, 75, 50. What is the surface volume mean diameter? 68.13, 78.15, 61.4, 38.16. Similar to the last problem, we need to identify what is asked and calculate. So this is same as the last problem. So just take a minute and understand what is being asked and then answer the question. So, well, I'll go with the answer. The answer is 61.4. So we'll see how the answers. First, we have taken the size range and mass of particles in that size range, and we have calculated first dpa, because particle mean diameter is not given over here directly, and mass fraction again is not given over here directly. So first we have calculated the DPI. DPI is 7. What is 704 plus 352 mean? You people might be aware from the mechanical unit operations class. So minus 704 plus 352 mean that it has passed the minus 704 C. I mean 704 micron C, but 352 it has retained. So meaning the particle is greater than 352 but smaller than 704 micrometers. So this is what is meant over there. And so we are taking the average 3704 plus 352 we have taken and divided by 2. That is 3704 plus 352 divided by 2 is equal to 704 plus 352 divided by 2. I think we need a bigger table, but yeah, fine. Is equal to, I mean, I don't think 52 plus 176 divided by 2. 176 plus 88 divided by 2 is equal to, and 88 plus 44 divided by 2 is equal to, and this is 44 divided by 2. This is how we calculate the DPI. And after calculation of DPI, what we need to know? We need to know the mass fraction of the material. So for that, we have calculated the mass of the particles in the size range, and we have summed up the mass, and it has come out down to 250 grams. And this 250 we have divided 25 by 250, 37.5 by 250. This is 25 divided by 250. 37.5 divided by 250. In this manner, we have calculated the xi, and after that we have calculated the xi by dpi, and we have summed up the values. So this has come down as 162.889. So we all know the volume surface mean diameter is given by this volume surface mean diameter is equal to 1 by xi by dpi. I mean summation of xi by dpi. So summation of xi by dpi we all know, and substituting back in the formula we get the value as 61.3927 micrometer, which is nothing but 61.4 micrometer. So similar problem, similar to what we have solved in the last thing and this problem. So now we are moving on to question 8. Before that, let us take a short break. Now the time is 3:59, or yeah, time is 4 now. We'll just wait till, I mean, give me 5 minutes, and not 5 minutes also, because we have a long thing to cover. So 4 p.m. now, and I'll be back by 3 p.m. Yeah, we'll resume the session now. So, question 8. So, question 8, it is about Eoto's number. So, we'll yeah. Um, Significance of Eoto's number is ratio of gravitational to surface tension forces, and ratio of gravitational to inertial forces, and ratio of gravitational to capillary forces, and ratio of gravitational to viscous force. Answer is gravitational to capillary forces. Yes, Eoto's number has a significance that it relates the ratio of gravitational force to the capillary forces. So significance of Eoto's number is that it relates it is the ratio of gravitational force to the capillary forces. So answer is option C. Now another one problem, it would be interesting here. It is similar to the problem that we have seen and we have solved in the last two things. So the first thing is finding out the diameter, I guess. And the question 9, it is asked that size analysis was carried out on a sample of gravel. The mass mean diameter of the sample to the nearest integer is dash mm. The mass The mass mean diameter of the sample to the nearest integer is dash mm. The data for mass fraction and average particle diameter of the fraction are given in table below. So XI and DPI data are given and we are asked to find the mass mean diameter of the sample. So XI is 0.2, DPT is 5 and for 0.4, 10, 0.4, 20. So here instead of giving the mass, they have given directly the mass fraction. So it has made our thing easier. So first we need to identify what formula mass mean diameter belongs to. So till now we have solved for the volume surface mean diameter. So now we are asked to solve for mass mean diameter of the sample. So therefore mass fraction is given and dpt is given. So mass fraction is 0.2, 0.4, 0.4 and here it is 5, 10 and 20 mm. So mass mean diameter formula is nothing but we have xi into dpa. So till now we have seen diameter as xi 1 divided by summation of xi by dpi, but here it is directly xi by into dpi summation of xi into dpi. So answers options are 14 mm, 16 mm, 11 mm and 13 mm. So the answer to this particular problem is 13 mm. So we'll directly jump on to how it is solved because there is only 1 hour left and we have around 20 more questions. So first we know the xi, we know the dpt, and here it is xi into dpi, it is 0.2 into 5, 0.4 into 10, 0.4 into 20. So summation 1 plus 4 plus 8, 8 4 12 13. So summation is 13. So mass mean diameter is given by summation of xi into di and therefore D is 13 mm. So it is a direct problem, so it is easier to solve. And let us go on to question 20. Question 10. In question 10, we have, consider a cylinder of diameter D and length D, a sphere of diameter D, and a cube of side length D. Which of the following statements concerning the sphericity of the above objects is true? So we are asked to compare the sphericity of a cylinder, a sphere, and a cube. In previous problem we have identified the sphericity of a cylinder, and now we are asked to identify the sphericity of a cube and then compare with the sphericity of a sphere. For sphericity value of sphere is nothing but 1 always. It is the thing to which we are comparing. What is the formula of sphericity? Sphericity is nothing but the surface area of the volume equivalent sphere to the surface area of the actual particle. So in case of spheres, both the values are same. So it becomes 1. So sphericity therefore becomes 1. So we will see the options first. First one is sphericity of sphere is greater than cylinder and greater than cube. And second one is sphere and cylinder, cube, everything have same sphericity. And third one is sphere is less than cylinder is less than cube. And third one is, last one is cylinder is greater than sphere and which is equal to cube. So here I would like to mention one thing. Always sphericity of sphere is 1, and all the non-spherical particles have sphericity less than 1. So sphere has the highest sphericity, that is 1. So it should always be higher. And so based on that condition itself, we can eliminate all the other options. Sphericity of sphere is cylinder or cube. Cylinder and cube would not be having a sphericity of 1. Just remember that. And at last, third one is sphericity of sphere is less than cylinder and cube has having highest. Again, it is false. So on these conditions of preliminary examination itself, we can eliminate all the options and go with option 1. That is, sphere is greater than cylinder is greater than cube. Option A is the right answer. But for more in-depth analysis, we need to identify what is the sphericity of cylinder and what is the sphericity of cube. So for that, we are going through this particular means. So first one is cylinder, which has diameter D and height D. So I think we can go with previous base. No, I'll go with that itself. What was the question we were solving? I think 14, right? Oh my god, we have a lot of questions to solve, guys. I don't know why I took these many questions. I thought there would be time, but I think we would be running out of time. But it's okay. We are still, see, we have 57 slides and we are still in slide 19. Great work. So, okay, volume of cylinder is pi r square L. So, here everything is D. So, it is pi by 4 D square L and pi by 4 D cube. So, volume of cylinder is pi by 4 D cube and surface area of cylinder is again given by this formula, and we are substituting R is equal to D by 2 and L is equal to D. So, we are getting the value of surface area of cylinder as 3 pi by 2 d square, 3 by 2 pi d square or 3 pi by 2 d square, whatever. And volume of sphere is 4 by 3 pi r cube and it is pi by 6 d sphere cube. Volume equivalent sphere diameter is equal to pi by 4 d cube, 4 by 3 pi by 6 d cube. Oh my god. Pi by 6 d cube is equal to 3 pi by 2 d cube. Pi by 4 d cube. What I have given? It is pi by 6 d cube is equal to pi by 4 d cube. And Therefore, d sphere is equal to, all other terms would go into the other side. I hope now we are clear. So pi by 6 d sphere cube is equal to pi by 4 d cube, and d sphere is equal to pi by 4 d cube into 6 by pi, the whole power 1 by 3. It is equal to 1.414470, and surface area of sphere with same volume as cylinder is equal to pi 1.3104 d square, and sphericity is surface area of a sphere with same equivalent volume to the surface area of the actual particle. Sphericity of cylinder is therefore is equal to this one divided by this one. Now, so we got the sphericity of cylinder as 0.8736. Now, next we need to identify the, oh my god, cube. Side length is d. So, volume of cube is d cube and surface area of cube is 6d square. And volume of sphere is 4 by 3 pi r cube and pi by 6 d square d sphere cube. And again, volume equivalent sphere diameter calculation. So here what are we going to do? Pi by 6 d sphere cube is equal to 6d square. And this becomes equivalent to this d sphere is equal to this one. I hope you are understanding the substitution. It is nothing but what we have done in the last one. And surface area of sphere with same equivalent volume as the particle is equal to pi d sphere square, and it is given by pi 1.5393 d square. So sphericity of cube is again given by this formula, same formula, and we are calculating the sphericity of cube as 1.5393 into pi d square divided by 6d square, and it gives 0.8055. So 1 is greater than 0.8736. 36 greater than 0.8055. I hope you are now clear with question 10. Now we'll go on to question 11. What would be the aspect ratio of a particle having length 4.6 centimeter and width 7 centimeter? First one 1.62, second one 1.52, third one 1.92, fourth one 1.32. So aspect ratio is nothing but the maximum length divided by the minimum length. So here maximum length is width, that is 7 centimeter, and width length is 4.6 centimeter. So how are we going to calculate the aspect ratio? Aspect ratio, we are going to divide the width by the length. So it is 7 by 4.6 centimeter, which is nothing but 1.52. So answer is option B, that is 1.52 is the right answer. Aspect ratio is nothing but one of the parameter that we use to define the particle shape, and here it is defined as the ratio of width to length. Mostly it would be largest dimension to the shortest dimension, and here it is 7 by 4.6 and it is 1.52. So answer is 1.52. Now we go on to question 12. In question 12, it is asked that which among the following mean diameter can be used in the field of hydrology? First one is arithmetic mean, second one is Sauter mean, third one is volume mean, and fourth one is de Broglie. Answer is arithmetic volume mean. Sorry, answer is volume mean, and we'll just see which mean is used where. So here the question about is about which mean can be used in the field of hydrology, and the right answer to that particular question is volume mean. So question 12, the answer is volume mean. So where do we use the other mean diameters? So first one is arithmetic mean we use in the application of evaporation, and second one is sorter mean we use in the application of absorption. Third one is volume mean we use in the field of hydrology. That is what is asked in this particular question. That is which type of mean diameter is used in the field of hydrology. The right answer to that particular question is volume mean. Last one, debrook, it is used in combustion, equilibrium, spray system, etc. So it is a theoretical question. Again, it is covered in the syllabus. So I request you all to please keep an open eye in whatever is being taught in the lecture by the professor. So these questions can come in your final exam also. So please be aware of that. And yeah, first question 13. Question 13, it is widely used catalyst for partial oxidation is platinum gauze, P2O5, SiO2Al2O3 and NiAl2O3. Again, this is a question which is being theoretical question and is widely asked also. So please don't skip the theory part in the lecture and be aware it might come in your final exam also, or it might come in your assignments also. So the right answer is V2O5. So we'll see which is Vidova is used for partial oxidation as catalyst for partial oxidation. But what about the rest? So we'll see that as well. So platinum gauze is used in ammonia oxidation, and V2O5 is used in partial oxidation, which is what is asked in this particular question. And the last one is SiO2Al2O3 is asked used in cracking. So and last one is NiAl2O3, it is used in hydrogenation. So all these things are being used so in these applications. So that's it. Last one is not last one, question 14 is again a theoretical question. Which hydrocracking catalyst is explicitly designed for the second stage environment to maximize diesel yield? So the coming up questions will mostly be theoretical questions. So I request you to keep an open mind and be aware and be attentive also, because it might come in the exams and you need not be revising again and again if you are listening now. So already these things are being taught in the class, so it should just be a revision for you guys. And so the first one is HC140LT, second one is HC205LT, HC120LT and HC185LT. So the question is about which is explicitly designed for the second stage environment to maximize diesel yield. HC205LT is the right answer. Hydrocracking catalyst HC205LT. Minimize second stage environment. Explicitly designed for second stage environment to maximize diesel yield. HC205LT. So where are the rest of these rest of the items are being used? So 14 first one 140LT is used as used in engineered to flexible naphtha distillate production, and HC205LT designed specifically for the second stage environment to maximize diesel yield, which is asked in this question. Third one 120LT is used in maximum total distillate production with improved cold flow properties, and fourth one 185LT is used in high activity catalyst with application for both naphtha and flexible diesel production. So I aware some of you might be very having difficulty in memorizing certain things in the that doesn't involve more conceptuals. Like this question and the previous questions, it is more of a theory and you need to keep certain things in mind. So there was this particular thing, um, like even I have some difficulty in associating certain things and remembering these for a very long period. So what I saw recently is that uh, you can associate certain things to certain portion of your memory, and from there it would be easy to recollect at later stage. For example, if you are seeing 140 lt, you can uh, associate that 140 lt to something and remember that particular thing and remember that in particular location in your brain. So it would be like you can keep everything and remember everything. Like I saw this in something and I'm not sure whether it works for everyone, and they called it memory palace. So it just helps you to remember everything and build the memory. So it might be useful if you find it. I saw this in a series, so I'm not aware whether it really works or not, but however, if it is useful, useful. So now we'll go on to question 15. So the coming up questions will mostly be theory, so we'll see. Fluidization processes are advantageous for good mixing, more contact efficiency, large scale continuous operation, all the above. So answer is all the above, because fluidization, we have seen the advantages, right? It provides good mixing and it provides more contact efficiency, because the particles have started to move and have moved from their original location. The chances of the particles being in contact with other particles and being in proximity with the fluid has improved drastically, and therefore contact efficiency is also increased, and mixing is promoted because the particles now started behaving like a fluid, that is dynamic fluid. They being mixed is very high, and large scale continuous operation can be carried out with fluidized bed. So all the above is the right answer. Now we'll go to question 16. Again here it is saturation moisture content is defined as maximum moisture material can retain without becoming slurry, moisture at which material does not emit dust. And third one, tendency of powder to gain or lose moisture at a constant temperature. This we have seen in the previous question, tendency of more powder to gain or lose moisture at a constant temperature. Can anyone recollect what it is? We have seen in the previous question. So the answer is moisture sorption or desorption. And fourth one is none of the above. So the right answer to this question is saturation moisture content is defined as the maximum moisture material can retain without it becoming a slurry. So that is the answer. So now question 17. Crush strength is the measure of. Why are we studying all the particle properties? Can anyone say why we are studying? Why we are studying the particle properties is what I'm asking. So the course is about fluidization, and isn't it sufficient if we only study the fluidization? And yeah, I mean you people are aware that fluidization is nothing but mm, mixing behave. I mean, making the solids to behave like a fluid by passing the fluid. So we need to be aware of the particle properties to carry out the efficient operation, because if crush strength here is defined as the particle breakage as a function of time, imagine if the particles getting broken with respect to time inside the bed, it would be difficult to get actual requirement out of the fluidized beds, and also like cleaning up, post cleaning up would be a task. So we need to be aware of certain particle properties which might give us an idea to better handle them, or even give us a way to do proper management of these particles. So the first one is crush strength is a measure of option 1, freezing conditioning agents effectiveness in preventing cold caking, particle breakage force as a function of time, rock breakage strength required for the crusher, and none of the above. So answer to this question we have seen now only. It is particle breakage force as a function of time. So crush strength is that. And question 18, it is about particle size and concentration have a direct effect on the catalyst reactivity or dissolution rate, flowability and handling of granules, and stability in suspension, all the above. So again, as we have seen, why do we need to study the particle properties? Because it has certain advantages. So similarly, particle size and concentration, why do we need to know? Because it has a direct effect on catalyst reactivity and dissolution rate. Yeah, it has an effect on that as well, because size and concentration plays a role in dissolution and also reactivity of the catalyst, and the particle shapes and size plays a role in flowability and handling of these materials. And if put it in a suspension form, whether how it is behaving is also important, and whether they are stable or not, all these things we'll again look at using zeta potential. But for now, these things are important, so all the above is the right answer. So these are the particles which I have spoken about. It is irregular shaped particles. Like non-spherical particles, we can say cylinder is a non-spherical shape, cube is a non-spherical shape, and what else we have? Prism, pyramid, everything is a non-spherical shape. But we can associate certain shape parameters to those particles. So they are regular shaped particles. But whereas these particles, can you identify or give some shape parameters through these particles? No, we can't, right? We can't recognize the shape of these particles, so it is difficult. So question 19, it is about in the bulk of irregularly shaped particles. First one, equivalent sphere concepts works well. At least one dimension can differ significantly from that of the other dimensions. And third one, both A and B. Option D, none of the above. So by looking at the image, I mean this image is not part of the question, I would like to remind. So I just put it for your reference. So in the question, if it is asked in the exam, it might not be given along with the image. So the first one is in the bulk of irregularly shaped particles. So these all are irregularly shaped particles, and equivalent sphere concept works very well. When do you think equivalent sphere concepts works well here? No, right? We cannot use equivalent sphere because they are highly deviating, but still they have one dimension that is significantly differing from other dimensions. So answer should be option B. Yes, because at least one dimension can differ significantly from that of the other dimensions. Equivalence sphere concepts works well when that is in close proximity with that of sphere. That probably should be representing more close to sphere. For example, cube is somewhat related to sphere. Cylinder in some conditions may be related to sphere. But these irregularly shaped particles we cannot define by using equivalent sphere concepts. Rather, we are using at least one dimension is significantly larger from the other dimensions. This is in bulk of irregularly shaped particles, not with regular shaped non-spherical particles, but in bulk of irregularly shaped particles. So that is question 19. Now we will move on to question 20. In question 20, it is asked that for the adsorption study, which type of mean diameter is important? What is adsorption? One particle getting adsorbed onto the surface of the other particles. So from this concept itself, we can clearly say what is important for the adsorption study. We need to know about the surface of the particles. So keep that in mind, and we'll go through the options and find out the right answer. The first one is surface mean diameter, second one is volume mean diameter, third one is arithmetic mean diameter, and fourth one is all the above. So as I mentioned before, right now, what is important for adsorption study? What comes directly in your mind? Surface area comes directly in your mind. So whenever we are dealing with adsorption study, what we need to know, we need to be conscious of the surface area, and therefore what type of mean diameter is important? Surface mean diameter is important. Surface mean diameter is important, right? I hope you are clear till now. We have covered almost 20 questions and 20 more questions are there. We'll kind of rush it up now, because since these are theory questions, we can cover it in a short time. That is not an issue at all. So yeah, we'll now start. Question 21. In question 21, it is asked that particle size distributions are classified into number and volume weighted distributions, volume and intensity weighted distributions, number and intensity weighted distributions, all the above. So, particle size distributions, we have been saying particle size distributions, wherein we classify the size of the particles. As I've given the example before, there is a column of particles we are using in the fluidized bed, and the column and the particles are coal or any other mineral for that matter. Can you say that the bed of the particle has this particular diameter? No, we can't say that, right? Because it is, we cannot say that all particles will be uniformly sized. So we are giving some average distribution for those particles. So those average distributions can be like this particular mass is in this size range, or this number of particles is in this size range, or this volume of particles is in this size range. We can go with anything like that. So here the number and volume weighted distributions, yeah, we can go with that, wherein we can say that these many number of particles are in this many size range, and this many volume of this much volume of particles is in this much size range. Second one, volume and intensity weighted distributions, and number and intensity weighted distributions. Again, we can go with all these as well. So the right answer is all the above. I hope you are clear. Now we'll go on to question 22. In question 22, it is asked that for a spherical particle, the sphericity value is equal to 1, 0.5, 0.1, 1.5. By now we are very familiar. That is, what is the definition of sphericity? Can anyone say? I mean, I don't want you people to say now actually, but can you guess what is the sphericity? I mean, not even guess. You people already have a clear idea of what sphericity is. Sphericity is nothing but the ratio of the surface area of the sphere with same equivalent volume as that of the particle to the surface area of the particle. For spherical particles, they both will be the same, and therefore its value is 1. Also, we have the comparison value of 1 for spheres to be comparing the sphericity of the non-spherical particles. So sphericity of spherical particles is 1. Keep that in mind. And question 23, it should be 23, but anyways fine. Circularity of a particle outline is defined as the ratio of, similar to sphericity, circularity is another two-dimensional concept. Sphere, we are using a three-dimensional concept. Sphericity, I mean sphericity is a three-dimensional concept, circularity is a two-dimensional concept, because here we would not be requiring volume based information, you would be just requiring the surface area based information from the two-dimensional figure. So circularity is defined as the ratio of actual perimeter to the perimeter of an equivalent area circle. How we define equivalent volume when we are dealing with sphericity? Similarly, we are defining a parameter, that is equivalent area. From volume we calculated area, and from here we are, from equivalent area we are calculating the perimeter. That is the difference between sphericity and circularity. And sphericity is a three-dimensional concept, circularity is a two-dimensional concept. So circularity is defined as the ratio of actual perimeter to the perimeter of an equivalent area. And the first one is the answer. Second one, let us just go through the options as well. Convex hull perimeter by actual perimeter. Area bound by an actual perimeter. Area bound by convex hull perimeter. So convex hull perimeter is nothing but which is obtained by few points in the along the particle outline. And all the above, not all the above, but circularity in specific is defined as the ratio of actual perimeter to the perimeter of an equivalent area. So actually convex hull is nothing but, convex hull perimeter to the actual perimeter is a concept of convexity. Actually, you can check convexity. Now the answer is option A, that is circularity of a particle outline is defined as the ratio of actual perimeter to the perimeter of an equivalent area circle. Now we'll go to question 23. Zeta potential is a measure of magnitude of the electrostatic or charge repulsion or attraction, one of the key parameters known to affect dispersion stability, and applied to improve the formulation of dispersions, emissions, suspensions, all the above. So as I've mentioned in the previous slides, zeta potential is an important concept. And why do we need to know the zeta potential? Because it is actually all the above is the right answer. So I'll explain why everything is correct. First one is a measure of magnitude of electrostatic or charge repulsion or attraction. When we are putting a particles inside some medium, we need to know whether they have electrostatic repulsion or attraction, whatever it is happening, we need to know. So zeta potential measures that. Second one, it is a key parameter affecting dispersion stability. As I mentioned, we are putting something in a solution, we need to know its stability. And third one, apply to improve the formulation of dispersion, emulsion and suspensions. When we know the concept of stability of a suspension, we can use it in formulating dispersion, emulsion, suspension, whatever it is. So zeta potential is important because all of the three reasons are true. The first one is magnitude of electrostatic charge, repulsion or attraction. One of the key parameters known to affect dispersion stability, applied to improve the formulation of dispersion, emulsion, suspension, all the above. So all the above is the right answer. So now we'll go to question 24. In question 24, it is asked that a uniform particle size distribution of powder ensures a non-uniform dissolution rate, non-uniform sedimentation rate, uniform dissolution rate. So, and none of the above. So this question also we have discussed previously itself. What is our discussion? A uniformly particle size distribution of a powder. Why do we need to have uniform particle size distribution? Because if we have uniform size, we can say that it has uniform dissolution rate. Uniform particle size distribution does not ensure non-uniform dissolution rate or non-uniform sedimentation rate. Rather, uniform particle size distribution has uniform dissolution rate. Option C is the right answer. Uniform dissolution rate. So these things I think you people would be aware of, or just quick revision would be helping you get knowledge into it. So if anything, we can see. Yes, question 25. In question 25, continuous rubbing or grinding of the powder in a mortar with pestle to reduce the particle size is called pulverization by intervention, trituration, leviation, none of the above. So here what is given? Rubbing or grinding of the powder in a mortar pestle, and there will be reducing the particles. This is phenomenon. What is this phenomenon is called? It is called trituration actually. So we'll just see what other terms mean in the next slide. So pulverization is a common term, comminution, crushing, grinding, wherein an external force is applied to a material to destroy it and reduce it into pieces smaller than original size. So we apply an external force and thereby reduce the size of the material and destroy it into smaller pieces than the original size. That is known as pulverization. Like comminution, grinding, crushing, wherein we crush it using external things. Trituration is the name of several different methods used to process materials. It is a form of comminution. In other sense, it is a production of homogeneous powder material by mixing and grinding component materials thoroughly. In mortar and pestle, what we are doing, we are producing homogeneous powdered material. If we rub using mortar and pestle, the size distribution will be more or less uniform. Whereas in crushing and grinding, it would not be the case. We would be having lots of large particles and lots of smaller particles also. Uniform mixing, uniform component production will not be there. So homogeneous material production is happening in trituration. Leviation is the process of grinding an insoluble substance to a fine powder while wet. So if it is carried out by using wet, it is a leviation. So yeah, question 26 we will move on. In question 26 it is asked that according to Gelda classification, flour, cement are example of powder of the type. So I hope by now you are aware of Gelda classification of solids. Gelda classifies the solids into 4 categories: A, B, C and D. In C, they are very smaller particles. As you can see, it is classification is based on density difference between the particles in the fluid and the size of the particles. So very smaller size particles comes under C particles. They are cohesive in nature. Like very small particles, they would be highly cohesive, right? Second one is A category. A is like larger than C particles and these are easy to fluidize. And the last one, the third one is B. They are like larger than A particles and they are sand-like size particles and these produce bubbles. And last one is D and they produce very huge bubbles and it is very difficult to fluidize those particles also because it is difficult to control the fluidization of the gel D particles and potable particles. So according to Geller classification, flour, cement are example of the powder of type which one? C, A, B or D. So these flour, cement are very fine size particles, right? So they come under C size, Geller C classification. So option is type A, type B, type C and type D. So right answer is type C. So these things would be covered again in the coming up classes, actually Geller classification. So you need not worry if you don't know the right answer at this point. Actually, I would like to take a minute break. I'll be coming back. So yeah, sorry for the trouble actually. Yeah, we'll start now. Did anyone join in the meantime? Just checking. I don't think so. Yeah, we'll continue then. We have 15 more slides, guys, and 15 more minutes left. We should rush. It's okay. We'll see. If not, we can extend to 5-10 minutes. That's not an issue, if at all. So question 27, it is about, we saw the question 24, right? 26, yeah, it is 26. And now we are going to 27. Question 27, it is about drag coefficient in the turbulent flow regime is equal to. So you people might be aware that drag plays an important role actually. So in this particular slide actually, yeah, this one we have seen that drag force is greater than gravitational force. It is known as fluidized beds. If it is less than gravitational force, we call it packed bed. What is drag force? It is the pull that is pulling the particles from the packed state because of the fluid acting on that. So that is important. So here in we have Reynolds, based on Reynolds number, we have laminar region and turbulent region, right? So if laminar region, what would be drag coefficient, and turbulent region, what would be drag coefficients? In laminar it would be 24 by Re, and in turbulent region it would be equivalent to 0.44. So these things you would be studying after this also, so need not worry if you don't know the answer at this point. So first one, option 0.44, 0.22, 0.88, 0.11. So answer is 0.44 because in turbulent regime the drag coefficient is equal to 0.44. And question 28, it is about drag coefficient compares gravity and inertial force and viscous and inertial forces and inertial and capillary forces, all the above. So drag coefficient, we have seen that it is comparing gravitational force in some way. So answer is gravitational and inertial force. So we have seen that if drag force is greater than gravitational force, we are we are having fluidized beds. But if it is less than inertial force, if drag force is less than gravitational force, it is packed bed. So drag force compares gravitational force and inertial force. That is the particles before that. So here answer is gravitational force and inertial force. Some things if you don't know the formula also, you can just think and compare, and based on the concepts also you can answer the questions. So that is what I am saying. And 28, it is this question. And 29, attrition is the, what is attrition? Attrition we all know is the breaking up of the particles, and it is, they have given the definition, so we'll go by that and identify the right answer. Attrition is the collapse of dilute phase suspension into a dense phase flow, breakdown of particles, tendency for fine particles to be preferentially entrained from the reactor, none of the above. So attrition we all know it is a breakdown of the particles by some means. So it would be rubbing, so on so. So attrition here is the definition of the breakdown of particles. So the first one is collapse of dilute phase to suspension into dense phase flow, false. Breakdown of particles, this is the attrition. Tendency for fine particles to be preferentially entrained from the reactor, that is entrainment and elutriation, that is a different. All these things you will be studying as the course progresses. And the last one is none of the above. So answer is breakdown of the particles. So we'll go to question 30, and question 30 we have segregation is the property of particles to gather in different zones according to their size and density, to be preferentially entrained from the reactor, and to fall through gravity usually with co-current gas flow, and all the above. Segregation, as the name suggests, it is some form of separation mechanism that is happening inside the system. And so we have segregation is the property of particles to gather in different zones according to their size and density. So I am saying that segregation is a separation mechanism based on their size and density, or size or density, whatever this thing may be. It is a separation mechanism and it happens according to their size or density. And this statement is true. To be preferentially entered from the reactor, that is not segregation. As I told before, there comes two concepts, entrainment and elutriation. This comes at the later stage of the course. So this one is related to that. And to fall through gravity usually with co-current gas flow. Again, this is not true. This things all the above. This is some other name. You would have gone through this in the course. So answer is to gather in different zones according to their size or density. Size and or density. That is segregation. So it's question 31. It is at a very low gas flow rate, frequency and size of the bubbles formed are primarily governed by. So here note the important keyword, very low gas flow rate. So gas flow rate is very low. If at very low gas flow rate also the bubbles forms, what is the things that was affecting the frequency and the size of the bubbles formed? The first one, surface tension of the liquid. Second one, buoyancy or force of the bubble. Third, both A and B, and D, none of the above. So at a low gas flow rate, if frequency and size of the bubbles are primarily governed by surface tension of the liquid as well as the buoyancy force of the bubble. This is what is happening. So option A and B, both A and B is the right answer. So I mean this happens at a very low gas flow rate, so you must be conscious of that as well. Very low gas flow rate. So these things I am saying you will be studying in the later stage of the course as well. So that time this is just an introduction. You just need to identify a few things, like here the keyword is very low gas flow rate, and while with progress of the course you will be having a very deep understanding. So now we go on to question 32. In 32 it is asked the drag coefficient in the Stokes law region is equal to, as I have said before, what it is, It is 24 by REP. CD is equal to 24 by REP in the Stokes region, and turbulent region or Newton's regime, it is 0.44 for spherical particles. You must be aware this is for spherical particles. First one 48 by RE, second one 24 by RE, third one 64 by RE, the fourth one 16 by RE. Here RE is particle Reynolds number, that is REP or RE is equal to rho density of fluid into V into dP by mu, rho V dP by mu. So it is V is the velocity of the particles. So here again we are taking 24 by REP, drag coefficient in the Stokes law region is 24 by REP. I hope it is clear. Now we'll go to question 33. In 33 we have spherical particle is settling through a stagnant column of liquid. The terminal settling velocity of the particle is proportional to diameter of the particle, proportional to the square of the diameter of the particle, proportional to cube of the diameter of the particle, and it is none of the above. So at equilibrium, V is directly proportional to dP square into rho p minus rho f into g by 18 mu. That is the formula for the terminal settling velocity. What is terminal settling velocity? Terminal settling velocity is equal to rho p minus rho f into g into dP square by 18 mu. So it is proportional to square of the diameter of the particle. Option B is the right answer, proportional to square of the diameter of the particle. 34. Advantages of fluidization processes are good mixing. Yeah, it is an advantage. Less contact efficiency. No, in fluidized bed you have a increased contact efficiency. Third one, batch operation. No, it is a, you can use it in both batch or continuous, so it is not an issue. All the above. So right answer is good mixing alone. Advantage here is good mixing alone. Rest are not applicable for fluidization. So we go to question 35. In 35, at the minimum fluidized condition, the pressure drop through any section of the bed is equal to. So we have seen that with low velocity, the packed bed remains the packed bed. But with increase in velocity, at one point, the bed weight is equal to drag force acting on the particle. And this is known as minimum fluidization condition. And after that, the minimum bed starts behaving like the fluidized bed. So at minimum fluidized condition, pressure drop through any section of the bed is equal to weight of the particles, weight of the fluid in that section, weight of particles in that section, weight of fluid and the particles in that section, all the above. So the right answer is the weight of the fluid and the particles in that section is equal to pressure drop through any section of the bed. At that point, the particles will be loosely packed, but they would not be moving, but they would not be packed bed either. Till minimum fluidized condition, the pressure drop would be increasing with respect to velocity. After minimum fluidization condition, the pressure drop remains at constant. So question 36. Terminal velocity can be found from balancing the forces. Terminal velocity ut can be found from balancing the forces. Gravitational inertial forces per unit volume of particle, gravitational buoyancy and drag force per unit volume of particle, gravitational and drag force per unit volume of particle, and none of the above. So it is gravitational buoyancy and drag force per unit volume of the particle. So terminal velocity, it is like once at equilibrium, the particle's velocity, the particle has attained the equilibrium. When the particle is settling, like we have put the particle inside the column and we have allowed it to settle. What are all the forces acting on the particle? The particle experiences drag force, and the particle experiences gravitational force, and the particle experiences buoyancy force. So balancing all these forces, we can get the terminal settling velocity. So it should be balanced between gravitational force, buoyancy force and drag force. So question 37, it is, at the onset of fluidization, the voidage is larger than in packed bed, smaller than in packed bed, equivalent to that in packed bed, none of the above. So as I mentioned, till fluidized packed bed, the particle voidage is constant. It would not be increasing how much ever we increase the velocity. At minimum fluidization condition, the voidage would be comparatively higher. After it has crossed minimum fluidization, that is in the fluidized bed regime, the voidage is always larger. So even at minimum fluidization condition, voidage is larger, and after minimum fluidization condition, the fluidization regime, the voidage is larger. That is, the particles has expanded, so the bed height is increased. If particle has increased, the voidage, the region without the particle, has also increased. So it is larger than that in a packed bed. So answer is option A, larger than that in a packed bed. So here is what is fluidized bed actually. How many questions we have actually? Okay, yeah, right. We have only 2 more questions and 2 more minutes. It doesn't matter. We can finish. So here it is a fixed bed where we pass the fluid, gas or liquid, and bed height remains a constant. That is, this is the bed height LM. At minimum fluidization condition, you can see that velocity of fluid or gas has increased, and the bed has slightly expanded, and this is known as minimum fluidization condition. So till here it remains same for gas or liquid, the behavior. After that, if liquid, it is smooth fluidization. You can see there is no bubbles. The bed has uniformly expanded. This is known as length of fluidized bed. It is known as smooth fluidization. And the last comes the bubbling fluidization, and wherein we pass the gas with higher velocity and we are able to observe the bubble formation. So this is known as length of fluidization, but length of fluidized beds, but it has bubbles. Here smooth fluidization, there is no bubbles. Next comes the slugging, where the bubbles grow in size. You can see that smaller bubble, smaller, larger bubble, larger bubble, axial slugs, wherein it has almost increased to the size of the column, radius of the column. This happens with gas, bubbling associated with gas. And this bubble has almost grown in size with higher velocity, that it has, whole region has become without particles. This is known as flat slugs, axial slugs, flat slugs. After that, in turbulent fluidization, all the bubbles starts to collapse, and with higher velocity gas or liquid, the particles would be escaping the system and very leanly packed, lean phase fluidization with pneumatic transport. This is the fluidization regimes. So just to give you an understanding for the question that followed before. And next is question 38. In case of bubbling fluidization, which we have seen with the formation of bubbles when we were passing higher gas velocity, what is observed? Bubble size increases as gas velocity increases. Bubble size decreases as gas velocity increases. Bubble size remains unchanged as gas velocity increases. None of the above. So we were able to observe that with increase in gas velocity, bubbles also were growing in size. So bubble size increases as gas velocity increases is the right answer. So in case of bubbling fluidization, the bubble size increases as gas velocity increased. So option A is the right answer. So next is question 39. In a fluidized bed at the particular regime with further increase in fluidized velocity, the pressure drop across the bed increased, decreased, remains constant, none of the above. So as I mentioned before, till packed bed, the pressure drop increases with increase in the fluid velocity. After fluidization, the pressure drop remains the constant how much ever we increase the fluid velocity. So in fluidized bed at the particulate regime is nothing but after fluidization, but it is observed in a smooth fluidization with liquids or with low velocity gases. With increase in velocity, the pressure across the bed remains constant is the right answer. And last question for today's class, in case of churn flow, that is in bubbling regime, spherical bubbles formed, distorted bubbles forms, bullet shaped slugs are formed, none of the above. So we were able to see that in turbulent regimes, or before that we can call it as a churn flow, the bubbles were not uniformly shaped. They were not spherical. They were starting to get distorted. So distorted bubbles are formed is the right answer. Spherical bubbles start to get distorted, and we cannot say bullet shaped slugs. We cannot associate any shapes to it. So it is distorted bubbles are formed. Option B is the right answer. Distorted bubbles are formed. So yeah, that's it for today's class. If you have any doubts, you can ask now. I don't think it would be there actually. It should be fine. If you have any doubts, please ask, and I would like to take feedbacks also for this class. If there are any feedbacks, please put it in the below this. Actually, these videos are actually available for your viewing later. So if you have any doubts, you can post it there also. I'll be answering there. But if you have any doubts, you can use the forum for fluidization engineering NPTEL course. You can log into the NPTEL website and use the forum also. If it is related to the problem solving session, I'll be happy to take the questions there and answer there. And apart from that, if you have any feedbacks regarding the sessions handled by me, you can directly talk to me at the end of the sessions, or anytime during the sessions are also fine. I would like to know why no one is interested in joining the course also. I mean, not interested in coming to the live session. So if there are anything I need to know, I would be happy to take those feedbacks and would be improving them in the future. So thank you guys for attending. Mm, so yeah, thank you. If there are anything else, we'll meet in the next class. Today already it is already, yeah, already it is time has passed. So I'll stop the recording. So yes.